Chem Mastery. Your study buddies.
Hi all, we are Chem Mastery. Today is Friday. We are so happy to meet you all back. Today, I am going to discuss the last chapters, which is Chapter 8, Manufactured Substances in Industry. So, what is manufactured substance in industry? Almost everything we see is a manufactured product. Industrial products are manufactured for our comfort. In daily life, spoons, forks, pots are industrial products used in the kitchen. Washing liquids such as detergents are manufactured from ammonia. Bucket bottles, plastic plates, and bowls are examples of synthetic polymer normally used in our daily life. So, after going through this chapter, I hope you all will be more understand about the things around you every day and appreciate the beauty of chemistry. Today, I will cover all the subtopics which are alloy, glass, ceramic, and composite materials. Okay, let us start now. What is alloy? Alloy can be defined as a mixture of at least two elements with one of those elements being a metal. This means that an alloy can contain two or more elements. Okay. Let us see this diagram. The diagram on the left side is an iron, while the right is a stainless steel. When we mix iron, chromium, nickel, and carbon together, it can produce stainless steel through alloying process. The alloying process is important because it can prevent the corrosion of metal and alter the properties of a pure metal to make it harder and stronger. As you all can observe in daily life, many cooking appliances are using stainless steel as main material rather than using iron. This is due to the higher resistance to corrosion of stainless steel. That's why we are preferring to produce alloy nowadays. Now, you will watch a short video about the process of how to make alloys with metal and non-metal. Besides, the video will be explained about some properties of pure metals due to its orderly arrangement, which I will explain later. So, enjoy it!
In this video, we see how different metals bond together to form alloys, which still retain the metallic properties of the starting metals, but are usually stronger. Metal atoms are typified by having only a few electrons in their outer shells. This means that even when they bond, there's always room in this valence shell for more electrons. Each metal atom can bond with up to 12 others in a close packed lattice. Look at the red atom. It is surrounded by 6 in its plane, and 3 on top and 3 underneath. Less compact crystal structures are possible too, for example this arrangement where each atom is bonded to 8 others. Because there are still not enough electrons to complete the outer shell of any of the atoms, the electrons can move easily from one atom to another, making metals good conductors of both electricity and heat. And because the electrons are not localized in fixed bonds, the atoms can slide past each other, making them ductile, allowing the metal to change shape. It also means that when you try to react metals together, the atoms normally just mix into the lattice, forming metallic bonds with each other, and with no fixed proportions and randomly distributed. These structures are called alloys. Contrast this with compounds between metals and non-metals, or between non-metallic elements, where the proportions of each element is fixed. The oldest example of an alloy, perhaps, is the way bronze took over from copper in the early human communities of Europe around 6,000 years ago. During the late Stone Age, axes began to be made of pure copper, but they were fairly soft. When small amounts of tin were added to make bronze, you got an axe which was twice as hard and worked well. The Bronze Age had arrived. The atoms in a metal lattice are held by non-directional bonds, a sort of sea of loose electrons, as we said, allowing the atoms to slide past each other, still touching, making metals relatively easy to melt and bend, but hard to vaporize. When metals change shape, atoms actually slip over each other like this. However, this process does not happen all at once, but bit by bit, rather like trying to move a carpet by putting a ruck in it. Here is the way it happens in a metal. You see the slip moving easily one atom at a time where there's a dislocation in the lattice. It is this easy movement of atoms in the crystal lattice that makes most pure metals soft. Now put a smaller or bigger atom into the lattice, and this easy movement of the dislocation is blocked. See the way the bigger atom stabilizes the dislocation, which gets no further unless you put greater force, meaning that it's harder to bend the alloy.
After watching that video, I hope you all can have some basic ideas about formation of alloys and some unique properties of pure metals as well. Now, I will discuss about the arrangement of pure metal and alloys. A pure metal is made out of one type of atom that is of the same size arranged in an orderly manner. However, the layers of atoms in the pure metal are easily to slide over each other when force is applied. Thus, this characteristic causes pure metal to be ductile and can be easily to pull into the wires. Next, the pure metals are also malleable and its shape can be easily changed. As you can see in this picture, there are empty spaces between the atoms. So, when force is applied, the layers of atoms in a metal will slide to fill in the empty spaces and form a new structure. Now, let us see this animation. This is an animation about the arrangement of atoms in an alloy. Basically, an alloy is formed when different sizes of foreign atoms are mixed with the pure metal. This will disrupt the orderly arrangement of atoms in a pure metal and make the layers of atoms in an alloy be difficult to slide over each other when force is applied. Notice that there are two important terms mentioned in this slide, which are ductile and malleable. Some of you might be confused with both of these terms since they are quite difficult to differentiate. But don't worry about it, I will try to explain them now. The metals are ductile when the external force applied is tensile stress, either in the form of push or pull. Let's test a simple example in daily life. All you all have cable for charging phone, right? The copper wire inside the cables are said to be ductile because copper has ability to strengthen into a wire when pulled at the end without breaking. So, we will conclude that this type of material is ductile. As against, the malleability of metal is an outcome of compressive stress applied to it. It has an ability to form a shape when compressed. Okay, I will play a video about the comparison between ductility and malleability. Hope you all can be more understand after watching it.
In this video, I'd like to talk about two physical properties, malleability and ductility. Malleability is the ability of a solid to bend or be hammered into other shapes without breaking. If malleable, a material can be flattened into thin sheets by hammering or rolling. Examples of malleable metals are gold, iron, aluminum, copper, silver. Because metals are malleable, blacksmiths have been able to hammer metals into helpful objects over the years. Compare a malleable metal to this piggy bank, which is not malleable. Because gold is malleable, it can be fashioned into jewelry. Ductility is a physical property of a material with the ability to be hammered into thin sheets or stretched into wire without breaking. A ductile substance can be drawn into a wire. Again, most metals are good examples of ductile materials, including gold, copper, and silver. Aluminum is not very ductile. Copper is used to make wires, and gold can also be used to make wire. This glass is not very ductile. So there we go, 2 physical properties, malleability and ductility. Thanks for watching.
Hence, we can summarize that ductility corresponds to a change of metal into wires with the presence of tensile stress, while malleability corresponds to a change of metal into sheets in the presence of compressive stress. As I have mentioned during the previous slide, we can clearly know that the purpose of manufactured alloys is to enhance some certain properties. Firstly, alloys have lower melting point than pure metal. What are the reasons behind these properties? The first reason is the different size of atoms in an alloy make their arrangement less regular than a pure metal. This makes the bonds between the atoms weaker and lower the melting point. Next, the presence of a non-metal in it behaves as an impurity and restrict in rising to high melting point. That's why alloy has lower melting point. Alloys usually have shiny appearance. This is because alloying helps to keep the metal surface shiny and it prevents the formation of metal oxide. Next, alloy is harder and stronger due to the presence of foreign atoms. Alloy is made up of different sizes of particles. They have foreign atoms to disrupt the orderly arrangement of atoms of the pure metal and hence prevent the layers of atoms of the pure metal from sliding easily. Last but not least, alloys have higher resistance to corrosion because it is sufficient reactive to form a protective layer over the top of the surface of the metal. This barrier limits oxygen and air getting past the surface of the metal and penetrating the inner structure. So, alloys always will be the better choice than pure metals. Now, I will share some extra knowledge about alloy. There are 2 basic types of alloys, which are substitution alloys and interstation alloys. The different size of the atoms involved typically determine whether an alloy will be substitutional or interstation. As you can see, there is 2 models of substitution alloy and interstation alloy respectively. The black color is the atoms of pure base metal and the green color is the foreign atoms, which are also known as alloying agents atoms. In substitutional alloys, the different types of atoms are all about the same size. The alloying agents atom, which the green color, will substitute pure base metal, which are black color, without too great distortion of the crystalline structure. In interstation alloys, the different types of atoms are not about the same size. Alloying agents atoms try to fit themselves well in the interstation spaces, which the gaps between the atoms form in the crystalline lattice. No substitution will be taken place. Hence, It is obvious to order that the arrangement of alloys and pure metals are totally different. The uses of alloys are based on the composition and the properties of the alloy produced. Alloys are manufactured for specific purpose. Scientists change the elemental composition to produce alloys with different properties. Aluminium metal is the main composition of the duralumin alloy, as containing about 93% of aluminium. Duralumin is stronger, low density, and does not rust easily. Due to the properties of low density, it is lightweight and easy to move. Hence, duralumin is very suitable to be used for making aeroplane body, electric cable, and racing bicycles. Next, bronze and brass originate from the same pure metal, which is copper. However, both alloys have the same properties but are used for different purposes. They are stronger than pure metal, since the arrangement of atoms inside alloys is different from pure metal. Besides, they have high resistance to corrosion and have shiny appearance. Bronze is mainly used for metals, monuments, and trophies. For brass, it is commonly used for decorative purposes, primarily because of its resistance to glue. It is also commonly used to make musical instruments due to its high workability and durability. Steel and stainless steel are having same pure metal, which is iron, but the composition of iron in steel is much higher than stainless steel. Steel is made by adding iron to carbon, which hardens the iron. It is also known as carbon steel, which has high carbon content with low melting point. So, steel is characterized by its hardness and malleability. This alloy is mainly used for structure of buildings, bodies of cars, and railway tracks. On the other hand, stainless steel has a high chromium content that forms an invisible layer on the surface of the steel to prevent it from staining, which means that it has high resistance to corrosion. It is suitable for making cutlery and sinks, as the coating of chromium on stainless steel makes it attractive in its natural state without needing to be painted. Lastly, pewter contains a high content of thin metal, which is 95%, so it is stronger, shiny, and does not rust easily. The use of pewter can be started from Bronze Age and commonly used from decorative metal items and tableware in ancient times. Nowadays, we are mainly using pewter to make trophies, souvenirs, and also decorative ornaments. The different alloys can be produced by varying the composition. Now, let us watch this video about some common alloys being used in our life.
Look at some well-known alloys. Bronze, 3/4 copper, quarter tin, for sculptures, boat hardware, screws and grillwork. Brass, 70% copper, 30% zinc, musical instruments, coins, door knockers. Carbon steel, 99% iron and up to 1% carbon for building construction, tools, car bodies, machinery, rails, etc. Stainless steel, iron with about 18% chromium and 8% nickel, used for tableware, cookware, surgical tools and so on. Aluminium alloys for planes contain a few percent of copper or other metals. Amalgam is mercury with silver and other metals once used for dental fillings. Solder, lead and tin for joining electrical wires and components, melts very easily. Gold is usually an alloy containing another metal such as silver for increasing hardness. The number of carats, K, defines how many mass parts of pure gold are found in 24 parts of the alloy.
After discussing about alloys and its uses, let us proceed to the next subtopic, which is glass. Glass is one of the most versatile and oldest materials in the building industry. A lot of things surround us are made from glass. So, what is glass? Glass is a mixture of metallic silicates like pure sand, soda chalk, and an alkali metal. When silica is heated together with other chemicals, various types of glass with different properties are obtained. However, all types of glass have the same basic properties. One of the most common properties is hard but brittle. This is because glass only has almost fluid structure and do not have planes of atoms that can stick over each other. Hence, it will crack when excessive stress is applied. Next, it is chemical inert. This means that it will not undergo any chemical reaction, making it an ideal material for manufacturing laboratory apparatus such as beaker, measuring cylinder, and so on. Besides, glass is transparent. Because photons of visible light can travel through glass instead of being absorbed or reflected. It is also waterproof, as water cannot penetrate through it. Glass is used as heat insulator and it conducts heat at much slower rates. Lastly, glass has electrons that are held tightly with each other, thus prevent the flow of electric current in other materials, making it as an electrical insulator. Now, you will learn about the types of glass, which are fused silica glass, solder lime glass, borosilica glass, and lead crystal glass. First one is fused silica glass. It is made from silica without adding any other chemical. It has high melting point, which is 1018 degrees Celsius, so it requires high temperature to melt. Next, it exhibits less thermal expansion characteristic, and it does not expand nor contract much when there is a large change in temperature. Fused silica glass is mainly used in making telescope lenses due to their ability to transmit light in the visible, ultraviolet, and infrared range. Next, soda lime glass is composed by silica, soda, and limestone. It has a low melting point around 1000 degrees Celsius due to the presence of soda lowers the melting point of silica. Soda lime glass is produced on a large scale since it is easy to mold and used for producing glass containers such as bottles and drinking glasses. Its light transmission properties as well as low melting temperature make it suitable for use in window glass. Its smooth and non-reactive surface make it excellent as containers for food and drinks. However, it is easily cracked upon temperature change. Next, let us discuss about the next glass. There are a total of 5 components contained inside the borosilica glass, which are silica, soda, limestone, boron oxide, and aluminum oxide. Due to its resistance to heat, borosilica glass is used for making many laboratory glassware. These glassware do not crack easily upon temperature change because of its low thermal expansion coefficient. So, it is useful in many applications mostly involved with temperature changes. Last is lead crystal glass. Since the name of this glass contains lead, it definitely will have lead inside its compound. Lead crystal glass is made up of silica, soda, and lead oxide. The addition of lead also provides an improved look to the finished product through increasing the reflective index and density of the glass, making it clearer. The term crystal is misleading, and there is no crystal structure within the glass, as it is an amorphous solid, meaning that the arrangement of the element in glass is variable and held together by tight chemical bonds. Besides, lead replaces calcium to produce glass that is softer and denser. Rich crystal glass is suitable to be used in making prisms. Now you will learn about ceramics, and it has quite similar basic properties with glass. A ceramic is an inorganic non-metallic solid made out of either metal or non-metal compounds that have been shaped and then hardened by heating to high temperature. The atoms in ceramics are bonded by strong covalent bonds and ionic bonds. Besides, it is hard and strong due to strong chemical bonding. Next, ceramics are chemical inert, which means that they are unreactive with chemicals. In a ceramic, the atoms are tightly bonded in indefinite arrangement. If you apply too much force, the only thing a ceramic can do is break apart. The energy has nowhere else to go. The electrons in ceramics are all busy binding atoms together, and they are non-spared for carrying electricity and heat. That's why ceramics tend to be a good insulators, as the electrons are unable to move freely to conduct electricity or heat. For your information, there are two types of ceramics, which are traditional ceramics and advanced ceramic. At first, I will discuss about traditional ceramic. It is made from clay-based material dug from the ground, such as kaolin, that mixed with water to make it soft and flexible and squash into desired shape. Then heat the mixture at a very high temperature, about 1200 degrees Celsius, to produce ceramic. The composition of the clay used, type of additives, and varying temperatures determine the nature of the end product. Generally, traditional ceramics are used to make bricks, pottery, and crockery. Next, advanced ceramics are not generally clay-based. They are made from inorganic compounds such as oxide, carbons, and nitride. Advanced ceramics materials are now well established in many areas of everyday use due to its properties. They have higher resistance to heat and absorption, more chemically inert, and have superconductivity properties. Advanced ceramics enhance our life by their constant usefulness. They play a critical role in electronics, telecommunications, manufacture, transportation, medicine, defense, and space exploration. Advanced ceramics such as silicon carbide are used to making cutting discs due to its hard and strong properties. Silicon dioxide is also used to make brake discs because it can withstand thermal shocks and high resistance to heat. Advanced ceramics are also needed to make tungsten cable rings because it is hard and resistant to absorption. Now, I hope that you all are able to understand what ceramics and glass is. Let us do some comparison between ceramics and glass. As we can see, glass is transparent, whereas ceramics is opaque. This is because only very little light can travel through the ceramics without being absorbed, thus making it opaque. Next, in terms of heat resistance, ceramic can withstand higher temperature than glass. When the heat is applied to both of them, glass will be softened while ceramic remains unchanged upon heating process, as the atoms in ceramic are closely bonded together. Hence, ceramic cannot be melted or remolded since they are good thermal insulators and do not expand greatly when heated. The main difference between porous and non-porous surfaces are their ability to hold water, air, or other liquids. A porous surface has pores which allow things to flow through them more readily versus non-porous materials which have a tightened cell structure preventing ease of flow. As again, glass can be melted or remolded. Lastly, glass is stated as non-porous item, which means that it can stand up better to cleaning, whereas ceramic is usually porous except when dense. Hence, ceramic tend to hold germs and third longer and require laundry as well. Now, we come to our last subtopics in this chapter 8, which is about composite materials. Composite materials have played an important role throughout human history, from housing early civilizations to enabling future innovation. There are many common examples of composite material in our daily life, such as tea inside our mouth. So, what is composite material? In definitions, a composite material is a material made for combination of at least two or more homogeneous substances, that is, matrix substance and strengthening substance. As you can see in this diagram, the dispersed phase is strengthening substance, which is dispersed in the continuous phase matrix. In simple words, the matrix substance surrounds and binds the strengthening substance together. Both components of a composite material have different physical and chemical properties. When combined, the composite material form has better properties than the original components. Composite materials have permeated our everyday lives, such as products that are used in constructions, medical applications, oil and gas, transportation, sports, aerospace, and many more. In this video, I will explain about 4 main composite materials and their uses. First is reinforced concrete, which has high resistance to corrosion and high compression strength. It is produced when strengthening substance such as steel bars and wire mesh is immersed in concrete, which is matrix substance for making concrete. Reinforced concrete is widely used in the construction of bridges, dams, and buildings. Next, fiberglass is produced when plastic is strengthening with glass fibers. This composite material is used to make helmets, car bumpers, and printer circuit boards due to its lightweight and durability. Thirdly, it is a common composite material that will be used in many daily applications but rarely see it in life, which is optical fiber. Optical fiber is the technology associated with data transmissions using light pulse traveling along with a long fiber in a series of total internal reflection. The core and cladding have different reflective indices to enable them to carry data in large capacity and not be influenced by electromagnetic disturbance. Metal wires are preferred for transmission in optical fiber communications as thinner travel with fewer damage. Optical fibers consist of 3 layers, which are matrix substance and 2 strengthening substance. The innermost is the core that is made out of silica fiber. The core is enclosed with second layer that is made out of glass or plastic. The outermost layer is made out of plastic that acts as a protective jacket. In application, optical fiber has replaced copper wire in video cameras and used as cables in computer network. The next composite material will be discussed is photochromic glass. It is formed when glass is combined with silver chloride and copper 1 chloride. When exposed to sunlight, photochromic glass darkens due to the presence of silver atoms, which prevent the light to pass through it. In dim light, copper 1 chloride in photochromic glass will cause the glass to become transparent again. Photochromic glass can absorb UV light depends on the light intensity. Hence, it is suitable to be used in making camera lenses and the windows of car and building. Here is the video of explanation of superconductor. Enjoy!
When an electric current is passed through a conductor, some of the energy is lost in the form of heat and light. The amount of energy lost varies depending on the individual material's electrical resistance. Some materials, like copper and gold, are great conductors of electricity and have very low resistance. Scientists discovered that the colder these materials are, the more conductive they become. But no matter how cold you make copper or gold, it will always show some electrical resistance. Mercury, however, is different. In 1911, when scientists cooled a sample of mercury all the way down to 4.2 degrees above absolute zero, its resistance abruptly disappeared. The first superconductor had been discovered. Gradually, more and more superconductive materials have been found that show zero electrical resistance below a certain critical temperature. And when resistance is zero, electricity is conducted perfectly without any loss, and a current can theoretically flow in a closed loop forever. This has been demonstrated by scientists who have sustained electrical currents in superconductive rings for years without any measurable depreciation of energy. And it doesn't end there. Not only do superconductors have absolutely zero electrical resistance, they also don't like to let magnetic fields pass through them. Instead, the field remains at the superconductor's surface. This expulsion of magnetic fields is known as the Meissner effect. You've probably seen the Meissner effect in action in science experiments that look like this. A magnet is set on top of a superconductive material, and at room temperature, nothing really special happens, but when the material is cooled down to its critical temperature, the Meissner effect kicks in, causing the magnet to levitate, as if by magic. But superconductors can be used for much more than cool science tricks. These materials are used today in MRI machines, super fast floating trains, and even particle accelerators. But we can't forget that these superconductors have to be kept at temperatures near absolute zero in order to function properly. This is a main limiting factor in the practicality of superconductors. Fortunately, scientists have been busy finding and creating materials that become superconductive at higher and higher temperatures. For example, some ceramic materials undergo a superconducting transition at high enough temperatures that they can be cooled down using relatively warm liquid nitrogen. These materials are known as high temperature superconductors, and they have revolutionized how and where we are able to use this technology. But still, always having to have liquid nitrogen at hand is extremely limiting. The goal for scientists is to create a material that is superconductive at room temperature. If we had room temperature superconductive wires for electronics, we'd be able to power devices using much less power. None of the energy would be lost as heat, changing the way the electronics are designed and built. This technology would allow for smaller and much more efficient devices. In 2015, researchers observed a material that, when placed under extreme pressure, became superconductive at around -70 degrees Celsius. This set the record for the highest temperature superconductor, but as of now, room temperature superconductors haven't been found.
Now, we have discussed all topics in this chapter. We hope that you all can have a better understanding about this chapter. As usual, there are a total of 8 tutorial questions provided at the end of the slide, and the answer for tutorial will be given next week. Last but not least, I believe that all of you are familiar with the rules of regulation already, right? So, this will be the last opportunity for you all to win the prize. I hope you all can perform well in the quiz, and the top 3 winners will be going to announce next week. Stay tuned for it. That's all for us. Thank you so much for paying attention to our videos and putting your effort throughout this time. We hope that you guys are enjoying in this. Goodbye.